Finally, let's look at another example that's a bit different from the first two. Here, we're given two vectors, x, a vector in Rm, and y, a vector in Rn, and we want to construct a matrix A in R to the m by n such that the ij element of A is equal to xi minus xj all squared. The question now is, how can we write this as a single matrix expression for A? In other words, how can we write A is equal to something without resorting to writing it index by index? Now, this is somewhat tricky, but to do this, let's first expand the terms in this squared difference here. So what we have expanding this terms here is xi squared minus 2xi yj plus yj squared, just writing out this expression. And let's look at each of these different terms individually. Starting with this one here, we want some matrix such that the ij element is equal to negative 2 times xi times yj. But we actually already know about a matrix that is of this form. It's just the outer product of x and y. So this term here, negative 2 xi yj, will be captured by negative 2 times the outer product of x and y transpose. Now let's look at this term here, which is a little bit trickier. What we want is a matrix where for all the different columns, this matrix has the term, in the first row it would be x1 squared for all the different columns, because here the ij element of A has xi squared regardless of what j is. The next row would have all the second element of x squared down to the m element of x squared in all the rows. So we want to create a matrix like this. Now, first of all, if we didn't have these square terms here, say we get rid of these square terms, well, then we can create this matrix here as the outer product of the vector x and the all ones vector. Right? This would take x, multiply it by the corresponding element of I, but that would just be repeating these elements of x, I guess in this case, m different times. This would be really 1 of size n, but it's obvious from how we write this here, so we'll just write x1 transpose. Now this creates a matrix like this, where these terms are not squared. To square them, we really want to scale every element, every row in this matrix, by the corresponding element of x. And the way we do that, remember, is to multiply by a diagonal matrix, where the diagonal entries are the entries of x. And that will give us this matrix here, where all the terms are squared. So the next element in our matrix is going to be plus diag x times x1 transpose. Finally, let's look at the last term here, the yj terms. And that's analogous to this case, except that we want the constant values of yi squared to be in the columns of this matrix. In other words, we want a matrix where we have the whole first column being equal to y1 squared, the next column being y2 squared, etc., up to yn squared. And using the same method as before, we won't be explicit this time, but this ends up being equal to, first of all, the outer product of 1 times y transpose. That gives this matrix without the squared terms. And then we multiply by diag y to get them all squared. So our final expression for A is A equals negative 2 times this outer product times diag of x times this outer product plus 1 y transpose diag y. Now, you could maybe argue over whether or not this is a simplified form. After all, it has more expressions in this form than we had in the original equation. But it still is giving just a single matrix definition for what this entire matrix is, which can be very useful, especially if you're writing code that has to form this matrix. Oftentimes, using matrix operations in a lot of languages will be much more efficient. And it's still quite good to know how we can go about writing something like this in a form where we don't need to write it out term by term, but we can just write it as one big expression here.